Welcome. I am Amir Zaidi from Delft University of Technology, and I am here to present our work, Local Surface Approximation Contours for Virtual Reality Stylization. This visual is a teaser of what this talk is about. First, let's start with an introduction, where I will explain our motivation for working on this topic. Educational illustrations, like the images on the right, are commonly used to present and explain concepts in books. Such illustrations are often stylized with bright colors with black line art. This style simplifies the illustration's content to be more easily understandable. Currently, applications in virtual reality do not use this style, even when it might be beneficial in educational contexts. We therefore set out to fill this gap and bring this style, specifically the line art, to VR applications. We would like it to look nice and not slow down rendering below 90 FPS. Existing work, online rendering, falls into one of two categories: model space or screen space. Model space methods look great on individual meshes, but are incompatible with geometry modifying shaders, and their performance does not scale well to detailed scenes with many triangles. Screen space methods, on the other hand, are only dependent on the number of rendered pixels and therefore fast, but existing work has not yet made noise-free and consistent stereo line art. That brings us to our method, which is a screen space method with a focus on line art quality. We take advantage of the existing G-buffers in deferred renderers. In these buffers, every pixel has an associated world space position and a world space normal. Positions and normals together provide a lot of geometric information. We combine them to locally parameterized surfaces from which we can derive the locations of feature lines on our geometry. The specific features we choose to look for are discontinuities between smooth surface patches. For every pixel in our output image, we want to know if such discontinuity exists, and if it does, draw a line through this pixel. Let's take the example of a single pixel P while rendering a camel. We load a 3x3 pixel region around pixel P, consisting of the 3D position and normal vectors from the respective G-buffers. For our example, we focus on an arbitrary 3-pixel slice of our 3x3 grid. Then, for every neighboring pixel of P, which we call Q hat, we fit a sphere on the position and normal of P and Q hat. We then find its radius and invert it for the directional curvature. We then use this curvature to predict the geometry in pixel Q, opposite from Q hat. This prediction will not match the ground truth values in the G-buffers on discontinuous surfaces. Therefore, we can directly draw the error of our prediction as line art. For this example of curvature estimates, this is what the directional prediction errors look like. To get from our input to output, we find the directional prediction errors, take the maximum of all directions, and blend that on top of our input image, which gives us our final look. Unfortunately, the method we described has some edge cases that we need to address with extensions. First, as we link curvature to normal vector differences, discontinuities between parallel planes are not detected because both quantities become zero. To solve this, we additionally search for sudden shifts along normal vectors. This search is then added to our directional prediction error. Second, we want stereo consistent feature lines in VR, but the base method has no guarantees for consistency between views. Occluding contours on smooth meshes are specifically problematic, as they can differ between views. We hide this by filling the space between and around contours with a black gradient. The spread of this shading is dependent on 1. The distance to the object, and 2. The distance between the contour in the left and right view. And last, we applied 3 steps of post-processing noise reduction. When a discontinuity is found, we run our method with pixels located beyond direct neighbors, and if that does not detect a discontinuity, we make the resulting line less opaque, as it indicates the existence of a single aliased pixel. We also apply directional non-local maxima suppression, preventing noisy, high-frequency geometry from generating large black patches. And finally, we reproject the left and right views to their opposite and remove noisy lines, which only exist in one of the 2 views. Now, let us take a look at some scenes in motion. First, we look at a simple example, with objects where triangles have constant normals. In this case, curvature is 0, and the result is a simple difference of normals, resulting in these sharp lines on folds. In a more general example, with smooth normals, our method nicely shows both contours and sharp edges. Features are temporally and spatially robust, highlighting important geometric details from the current viewpoint. We performed qualitative and quantitative evaluations for our methods. First, we compare the quality of our line art across resolutions to a Sobel filter and another line art method by Honks. We use 2 variants of our method, which we call base and full. The base version has the contour fade out and noise reduction disabled. Our method has consistent lines even going down to a quarter of the resolution, and the noise reduction helps to suppress the aliased lines at these lower resolutions. Further, in this example, our method nicely handles the table's legs, unlike the comparison methods. Second, we revisit our original motivation. We compare memorization and recognition of meshes between methods, as improvements in those aspects is evidence for educational value. We also ask study participants to rate the quality of the methods. And we compare the same 4 line art methods as before, and add standard GGX shading as a 5th method. Our findings are somewhat positive. Our base method, without any of the extensions, performs best in all categories. However, the full method is second, behind the base. Our theory is that the performance reduction from the extensions causes this, but we don't know for certain. For now, we only consider the base method when looking at the results. There are 3 statistically relevant findings after false discovery rate correction of 10%. Sobel is worse on both memorization and recognition than our method, and shading is worse on memorization. For the quality assessment, we asked participants to rate the 5 methods on 3 statements. All line art methods performed better than shading, and our method performed best. To conclude, we introduced a new line art method, which is simple to implement and gives high quality results. We added multiple extensions, which solve edge cases of the method, and we performed a user study, where we found evidence of the method's value in educational contexts. Source code and the demo on GitHub under an MIT license, so check that out if you're interested. Thank you for your attention.